Okay, let's begin a new topic or new set of topics, which is going to be basically magnetism. So, in other words, the statistical mechanics of magnetic materials. But in magnetism, as you probably know, there are many types of magnetism. For example, they are called diamagnets, paramagnets and ferromagnets. So, we will have to explain what these three different types of magnetism is and why we have three different types of magnetism. So, diamagnetism is a phenomenon that is seen in all materials. It basically comes about as a result of Faraday's law. So, if you apply a magnetic field to a charged particles that are moving, so there you will be setting up currents, and those currents will themselves produce a magnetic field which will oppose the applied magnetic field. So, in other words, so the phenomenon of diamagnetism is simply the idea that if you apply a magnetic field to a material, there is going to be an induced magnetic field created by circulating charges in the material, which will oppose the applied magnetic field. So, in other words, the magnetic moments, if you wish to call it that, are not intrinsic to the material, they are induced by the applied magnetic field. So, the stronger the applied magnetic field, the stronger the induced magnetic moment, and it is going to be in the opposite direction of the applied field. So, this is called diamagnetism. So, that is what I am going to be talking now. But then there is going to be later on we will discuss paramagnetism, where the charge carriers already have an intrinsic magnetic moment. So, you do not have to apply a magnetic field to create a magnetic moment, they already have a magnetic moment. For example, it can be because of the spin of the electron, which is an intrinsic magnetic moment, or it could also be because of the nature of the orbitals of the atom. So, if you have s orbital, then angular momentum is 0, but you can have p orbital where L equals 1. So, that will contribute to an intrinsic magnetic moment. So, if the outermost electrons have a non-zero angular momentum, then it will contribute to a net magnetic moment of the atom. So, spin and the angular and orbital angular momentum put together is responsible for an intrinsic magnetic moment, which leads to what is called paramagnetism. So, which we will come to later. Okay, so let us start off by discussing diamagnetism. So, the first correct theory of diamagnetism in real materials was given by the Russian physicist Landau. So, that is why it is called Landau diamagnetism, because it is his theory of diamagnetism in real materials. So, like I told you already, diamagnetism refers to the property that charged particles, namely electrons in a metal, acquire a net magnetic moment when subject to uniform magnetic fields due to circulating currents that are set up as a result of the magnetic field. So, this induced magnetic field is proportional to the applied field and it is in the proportionality constant is diamagnetic susceptibility, and it is negative, implying that it is in the opposite direction. So, actually in order to study this satisfactorily, we have to use quantum mechanics. So, this was realized by Landau a long time back, that the proper description of this phenomenon requires the use of quantum mechanics. So, we will have to understand what happens to charged quantum particles, that is matter waves, which are also charged particles, that how do they, the wave function of those particles, how do they change when you apply a uniform magnetic field. So, it so happens that this is a problem that you have to study in your quantum mechanics course, where you will have to ask your teacher who teaches you quantum mechanics to explain to you to calculate the stationary states by solving time independent Schrodinger equation of charged particles in a uniform magnetic field. So, when you do that, so I will just tell you the final answer. So, it is like I will just do fast forward and tell you the final answer, but then if you really want to know the details, you will have to consult a quantum mechanics textbook, which will tell you, because this, remember, this is a statistical mechanics course and I have assumed some knowledge of quantum mechanics. So, I cannot possibly derive the stationary states of charged particles in a uniform magnetic field. So, I will tell you the final answer which I am going to use. So, you please look it up, just find out how to derive this result. So, the idea is that see, if you do not have a magnetic field, you know that the energy of the charged particles is going to be this, and then the kx, ky, kz are the good quantum numbers. So, the wave functions are labeled by k vector. So, however, if you have a magnetic field, this is no longer true. So, if you suppose you apply a magnetic field in the z direction, so the only k which survives as a good quantum number is kz. So, the other two will no longer be good quantum numbers, rather they get replaced by an integer called NL. So, instead of having h bar squared kx squared plus ky squared by 2m, it gets replaced by harmonic oscillator energy levels. That is understandable, because you see in the z direction, that is parallel to the applied magnetic field, the charged particle is free to move. So, its energy continues to be free particle energy, which is h bar squared kz squared by 2m. But then in the xy plane, you see, that is when they see the magnetic field, they start going round in circles. Basically, there will be circulating currents. So, the circulating currents implies that there is a bound state. So, bound state, you see that there is an analogy you can make with harmonic oscillators. So, harmonic oscillators are also bound states. I am not saying that is a proof, but you can get a sense that this is the reason why the energy level looks like that of a harmonic oscillator, because the in the xy direction they start going round in circles. They cannot run away to infinity, they have to keep going round and round in circles because of the magnetic field, and as a result their energies become quantized, and they happen to have this harmonic oscillator form, and the frequency with which they go round and round is basically the classical frequency that you can calculate using classical mechanics, and that is called the cyclotron frequency. That is the frequency of the path of the classical particle. But the point is, these are the energy levels. So, kz is continuous, it can be minus infinity up to plus infinity. All right. So, like I was saying, the energy levels of the charged particles are described by these quantum numbers called kz and NL. So, the kz can be anything it wants from minus infinity to plus infinity, because that corresponds to free particles moving in the z direction. But NL is basically the quantum numbers that correspond to the bound states in the xy plane. So, I have told you already that the charged particles are forced to go round and round in circles because of the magnetic field in the xy plane. So, basically it is a bound state, so it resembles that of a harmonic oscillator. So, you can rigorously prove also that it is actually the energy levels of a harmonic oscillator, and NL are given by the integers 0, 1, 2, 3, etc. And the energy of the quantized energies are h bar omega c, where omega c is basically the cyclotron frequency, which is the classical frequency of the electron of the charged particle. So, if you treat the charged particles classically, you know what is the frequency with which they go round and round. So, that is basically the result of a detailed derivation that you will find in quantum mechanics textbooks also. But then this is the story of the energy levels, but you have to ask yourself, what is the other half of the story, which is the story of the wave function. So, what do the wave functions look like? I am not going to write them down, but I will tell you that there is a humongous amount of degeneracy. In other words, see, normally what happens is that for a given energy, for example, for free particles, if you think about it, that for a given energy there is of course a degeneracy, but if you decide to label the states in terms of these kx, ky, kz, and if you ignore spin, then there is no degeneracy. It depends on what you use to label the states. So, suppose you decide to label the states not in terms of the energy. If you decide to label it in terms of the energy, then there is of course a huge degeneracy, because for a given energy you can have different orientations of k which have the same energy. But suppose I decide instead to label the states in terms of k itself, then of course there is no degeneracy, assuming the charged particles do not have spin. But then here you see, that is the point, that even though I have decided to label the states in terms of the quantum numbers kz and nl, see here if I decide to label the states in terms of kx, ky, kz, which are the quantum numbers, then there is no degeneracy, that is for the free particles. But however, here even if I decide to label the states in terms of the quantum numbers that are contained in the energy, namely kz and nl, I will find that there is in fact still a huge amount of degeneracy that is left over. And of course, do not ask me where this comes from. This is, as I told you, a result of a detailed analysis, a proper analysis of the quantum mechanics of charged particles in a uniform magnetic field. So, these are called Landau levels. By the way, these are called Landau levels, and these were first derived by Landau. So, they are called Landau levels. But then, so now you have to see what is the degeneracy of this. So, even if you decide to label the states by kz nl, so what is the degeneracy? The degeneracy is given by this ratio, which you will have to take my word for it. Namely, it is proportional to the magnetic field and is proportional to the area of the sample. So, this is something like a flux, magnetic flux, magnetic field into area. This is the quantum of the magnetic flux. So, it's as if the degeneracy is basically it's counting the number of flux quanta that are penetrating your sample, right. So, the fundamental flux quantum is hc by 2e, and the applied flux, which is magnetic field which is applied times the area of the sample. So, that divided by the flux quantum is the number of flux quanta that are penetrating the sample. So, that is basically the degeneracy of these energies. So, that the huge number of linearly independent wave functions corresponding to the same energy E k z n l. Okay. So, I hope you followed what I was saying. So, that is what degeneracy means. So, basically for one kz and one nl, you have one energy and you do not have one wave functions, you have this many wave functions, different wave functions, they have the same energy. So, that is what degeneracy means. And this is basically a picture of how the classical trajectory would look like. If you decided to treat the particle classically, it would go round and round in a helix like this. So, as you very well know. So, now I am going to use this these final answers, that I am going to assume this, and then I am going to go ahead and use my machinery of statistical mechanics and try to calculate the entropy of a gas of fermions subject to a uniform magnetic field. So, now how do I do that? So, this is how I do it, and I have to conserve energy. So, this is my energy. So, notice that this is the total energy of the system, and that can also be calculated in this fashion. This is the energy of each particle, and this is the number of particles having this energy, and there is this J label, which is basically a label which tells you the degeneracy. So, it is 1, 2 up to that ratio n. So, that is what I was saying here. So, basically this is the number of electrons or whatever electrons having energy kz nl and being in that jth level of degeneracy. Okay. So, this is how you label the states actually. If you want to completely specify a state of a set of charged particles in a uniform magnetic field, this complete set of quantum numbers, it is not just kz and nl, but also if you include this j, which goes from 1, 2, 3 up to this ratio n, the script n. So, that constitutes the complete set of quantum numbers. So, because you have specified the quantum numbers completely, so the number of particles in a given quantum state can be either 0 or 1, because they are fermions. So they are either 0 or 1. So this is either 0 or 1. Okay. So that's why I have decided to sum over only 0 or 1, and I can go ahead and calculate the entropy. As usual, I am going to use my trick that I can write this as a Kronecker delta in terms of a integral over some angles, and then I do the summation, and I do the usual things here. So you should follow along with a piece of paper and a pen and try to work out all these steps, and you know why I went from here to there. So that's basically the saddle point approximation, where I feel entitled to replace theta by theta star, because that's the most probable value. So and the most probable values, they are as before, so the reciprocal temperature and chemical potential by temperature and so on. So finally I do all that and I get this answer for the total energy of the system and the total number of particles at a temperature T and chemical potential mu, and the entropy is derivable in this fashion. So notice that there is notice the sum. The sum is over Kz and NL, which are the quantum numbers of the energy of this particles, but it's also a sum over J, which are these additional quantum numbers which tell you the degeneracy of the various energy levels. Okay, so now I have to go ahead and see if I can calculate the Helmholtz free energy. So see, I am purposely trying to give emphasis in this course on the microcanonical approach, where in all the examples I first try to calculate entropy. So that I am doing that on purpose, because most of the other textbooks and other lectures, they kind of quickly migrate from microcanonical ensemble, which is focused on entropy. They directly jump to canonical ensemble, which is basically based on Helmholtz free energy. And of course that is justifiable, because finally those are the quantities that are of interest from a practical standpoint. But then I felt that in order to have a different flavor to the subject, different from what is readily available, I felt that it's nice to impress upon the audience that it's possible to do all this from from really fundamental first principles like microcanonical ensemble. But it's a matter of taste. You can go ahead and do it using canonical ensemble. As I've told you, those two are interchangeable in the thermodynamic limit. Alright, so now I'm really going to go ahead and calculate the Helmholtz free energy, because I'm going to use it to find what is called the diamagnetic susceptibility, which is defined in terms of Helmholtz free energy. So as you very well know, Helmholtz free energy is defined as internal energy minus absolute temperature minus times entropy. So that's how it's going to look like. And if I use this, so this is my entropy, and so this is what it's going to look like. So now the idea is that if I expand the free energy, so notice that everything is going to, n is fixed, but mu can depend on the magnetic field. So the number of particles is fixed, but the mu can change depending upon the magnetic field, and temperature is fixed, number of particles. So in the canonical ensemble, what is all fixed? Number of particles is fixed, temperature is fixed, and volume is fixed. So so in that sense, these things can change with the magnetic field and temperature, the chemical potential. So I can go ahead and expand the Helmholtz free energy in terms of the applied magnetic field. So I'll get a Taylor series in this fashion. So if I decide to do this, I'll get a Taylor series, and it so happens that in this example, the Helmholtz free energy is an even function of h. So it's going to look like this. So this is going to be 0. So that's also that's understandable in the following sense, that you see the susceptibility or the magnetization is basically the rate of change of Helmholtz free energy with the magnetic field, if you like. So, it is like magnetic moment, induced magnetic moment is proportional to df by dh. But we also know that if you turn off the magnetic field in a diamagnetic material, the magnetic moment should also go to 0, unlike in a paramagnet where it does not go to 0. So, if this is non-zero, then the rate of change of the Helmholtz free energy with magnetic field does not go to 0 as the magnetic field tends to 0. So, that is the reason why you should not be having this in a diamagnetic material. So, that is going to be 0 in a diamagnetic material. So, the series really starts from here, and this quantity is therefore proportional to what is called diamagnetic susceptibility. So, I am going to define this object more carefully later on, but basically it is the coefficient of the leading term in the Taylor series of the free energy with respect to the applied magnetic field. So, you expand the Helmholtz free energy in terms of the applied magnetic field, and the coefficient that appears in the leading term is basically proportional to the diamagnetic susceptibility. Now, that is understandable because like I told you, so diamagnetic susceptibility is basically defined as the induced magnetic moment, change in the induced magnetic moment for unit change in the applied magnetic field, and the magnetic moment itself is defined as the change in the Helmholtz free energy with the applied magnetic field. So, as a result xi m is proportional to d squared f by d h squared. So, now the question is, how do I do this summation? So, it looks nasty because firstly doing the summation over kz is not that difficult, because we know that kz is continuous, in the sense that, I mean, of course, if it is particle in a box, then it is not continuous, it is discrete, but you know that we are in the thermodynamic limit in the z direction. So, we know how to convert that into an integral. But however, these Landau levels are by definition discrete, so there is nothing continuous about them. So, we have to learn how to do discrete sums. But we are not good at that, because we know well, if it was a continuous integral, we know how to do that using saddle point and this and that, but if it is a discrete sum, we are stuck. So, it would be really nice if we could convert a discrete sum into an integral which we know how to do, right, using saddle point and so on. So, fortunately, there is in mathematics there is an identity which is called Euler-Maclaurin formula, which allows us to write a discrete summation such as this in terms of an integration, in terms of a continuous integration. So, I won't again derive this, I won't tell you the derivation, you will have to take my word for it, you will have to look up some maths books, or just take my word for it. So, it's just an identity from mathematics, and so I am going to try and use this to do the summation. So, I am going to define this as omega. So, this is also what is called the grand partition function. So, I mean, I'll touch upon this a little later. So, this also has a physical meaning, but right now it's just a symbol, it just means this sum. So, the question is, how do you do this? So, you see, notice that the quantity that is sitting here is independent of j. So, when I sum over j, this degeneracy, so it is just sum over all the degenerate states, and whatever I am summing over does not depend on that index. So, finally, what I get is the number of degenerate energy levels, which is the flux that is threading the system divided by the quantum of the flux. So, then whatever remains is basically the summation over kz, which I have converted to an integration, which is of course we know how to handle, but what we do not know how to handle is this one, which is the summation, a discrete summation over Landau levels. So, in order to do this, since I know how to do the integration over kz, I'm going to take the liberty of giving this a name. So, I'm going to call this quantity this. The reason why I call it this is because you see this energy is nothing but h bar squared kz squared over 2m plus so it's going to look like NL h bar omega c, then it's going to look like plus 1/2 h bar omega c minus mu h. So, I am going to put these two together and call it mu naught. Okay. So, the rest of it is this one. So, mu naught is this much. Okay. So, that is the reason why I have given it that name. Okay. So, whatever that is, I am now forced to evaluate this discrete sum in this fashion. So, now I am going to use my Euler-Maclaurin formula, and which allows me to rewrite. So, you please verify all these steps by yourself. So, this is using the earlier this result. So, I am going to use this result, which is Euler-Maclaurin formula. I am going to stop right here, I am going to stop there. So, I am going to use this, and so the first term is this one. So, this term that I am looking at, so the summation becomes an integral. So, this summation has become this integral, but then there is f0 term 1/2 of f0, and that is what this is, right. And then this is the first derivative, which is 1/12. So, 1/12, and I am this, and of course, the second derivative I do not care about. So, now I am going to rewrite in terms of, so if I decide to rewrite in terms of mu and not mu naught, this term cancels out. So, you please do this yourself. All I have done is, so instead of writing in terms of mu naught, I have written in terms of mu. So, when I do that, this term cancels out. So, this term cancels out. So, I will end up with this and immediately this. And notice that there is a change in sign, mainly because of certain conspiracies, and then this 1/12 will become 1/6. So, you please work this out yourself. Okay, I can't explain everything. So this can be a useful exercise to you to explain how to go from here to there. All right. So, now I am going to substitute that. I am going to substitute this here, and I end up with this result. So, notice that the Helmholtz free energy is so going back here. So, this is your omega. So, this is your omega h. So, basically its Helmholtz free energy is n times mu h plus omega h. So, which is what I have written here. So, its f h is n times mu h plus omega h. But then you see, if I decide to keep n fixed, which is of course what I am mandated to do, but then if I decide to keep n fixed and differentiate omega with respect to mu, so why is this the case? So, let me explain that to you. I will have to explain why this is. So, this is my omega z. So, now suppose I calculate d omega by d mu, suppose. So, there is a mu sitting here. So, what I will get basically is, so I see if I calculate d omega by d mu, so there is a mu sitting there. So, if I differentiate this omega, okay, let me do that here for example. Okay, so omega h equals, okay, minus t log 1 plus minus mu. Okay, so that is what that was. So, now suppose I want to calculate d omega by d mu. So, what is that going to look like? So, it is going to look like 1 by e raised to minus beta e minus mu times this one e minus mu. Then again if I differentiate exponential chain rule. So, if I differentiate the exponential with mu, I will get a beta out there. Okay, so, beta times mu is 1, and this is nothing but 1 over 1 plus e raised to beta e k minus mu. of course there is a summation over something which was there, the summation continues to be there, and this is nothing but you see minus n. So, this is the number of particles, this is the Fermi-Dirac distribution minus n. So, that is the reason why this is n is negative derivative of chemical potential with respect to mu. Okay. So, now I am going to use that. So, n is the derivative of this with respect to mu. So, if I differentiate with respect to mu here, so I get from so the derivative of this with respect to mu becomes this, and derivative of r dash with respect to mu becomes r double dash. Okay, and then there is a minus sign, where the minus sign goes away, becomes a plus sign there. Alright, so it looks very nasty, but let us proceed. You will see that the final answer will look quite simple. So, now that I know what n is, I am going to use this later. So, now I am going to go ahead and calculate omega, the derivative of omega with respect to h. So, if I do that, I get this result. So, basically I just have to take this, I have to repeatedly manipulate this formula. So, first I differentiate this with respect to mu, and I get formula for total number of particles. Now, I decide to differentiate with respect to h, which is magnetic field, then I get this formula, and then notice that I already have this. So, I can put these two together and write down a derivative of omega, the grand partition, with respect to the applied magnetic field, and it is going to look like this. Okay. So, now the change, the rate of change of the Helmholtz free energy with the magnetic field is given by this formula, because n is fixed. So, I just have to differentiate the chemical potential and the grand partition function. So, when I put them together, you see that this, which is nasty, which I would not have known, I mean it would have been hard for me to calculate mu dash, it drops out of my calculations fortunately. So, I end up with this nice compact looking formula for the rate of change of the free energy with the magnetic field, which is of course you should recognize that that is proportional to the induced magnetization. Now, so that is understandable, because you see it's basically proportional to the cyclotron frequency, which is proportional in turn to the applied magnetic field. So, the induced magnetization is proportional to the applied magnetic field, which is as it should be. So, now I differentiate again with respect to the magnetic field, and I end up with this formula for the second derivative. So, recall that that was the coefficient in the Taylor series, which was supposed to be proportional to the diamagnetic susceptibility. So, I end up with this result for that coefficient. So, I will have to find out what this is in order to complete my calculation. So, for that I have to go back to the definition of this R. So, R was this. So, when h is 0, mu 0 is same as mu. So, this is proportional to the magnetic field. So, if mu 0 0 is same as mu of 0, because this is proportional to the applied magnetic field, the cyclotron frequency is proportional to the applied magnetic field. So, so now as a result I can write down this. Okay. So, this is by definition. Then if I differentiate with respect to mu 0, I end up with this formula, and then I substitute that back into this expression, and I get this result. So, now finally I take the 0 temperature limit. So, at 0 temperature this becomes basically a step function. So, at 0 temperature beta tends to infinity. So, when beta tends to infinity, this whole thing is 0 if h bar squared kz squared by 2m is greater than mu naught, it is 0. So, basically I have to integrate only in situations where it is less than mu naught. So, in other words, I have to integrate. So, this is nothing but h bar squared kf squared by 2m. So, I am going to write this in terms of my Fermi momentum. So, I have to integrate from kz from minus kf to plus kf. So, that is the Fermi wave vector, and so this becomes 1 in that region. So, this is just Fermi statistics, and I end up with this result. Okay. So, that is what it is. So, notice that kz is from 0 to infinity, not minus, sorry, it is from 0 to kf. So that's how it's been. I mean, we have defined it that way, remember. So, so it's 0 to kf, so it's only kf which comes in the formula. So finally, we are ready to write down our formulas for the diamagnetic susceptibility. So notice that in the linear regime, the Helmholtz free energy per unit volume is basically induced magnetic moment times the applied magnetic field. So, so this would be in the linear regime. So in general, in the nonlinear regime, the induced magnetization is defined as the rate of change of the Helmholtz free energy per unit volume with respect to the magnetic field. So this is going to be my induced magnetic moment. So I further know that this is also proportional to, so f dash h is basically h times f dash dash 0. So that's because of the Taylor series. The first term is 0, as I told you, that induced magnetic moment is proportional to the applied magnetic field. So this we have taken a lot of trouble to calculate just now, and this is that. So finally I am able to write the induced magnetic moment as being proportional to the applied magnetic field, and the coefficient is called the diamagnetic or Landau's diamagnetic susceptibility. It comes with a minus sign, signifying that it opposes the applied magnetic field, and the final answer is this classic result, this 1/3. So without the 1/3 is basically what's called Pauli's paramagnetic susceptibility, so which I am going to discuss next. But right now this is the result which Landau derived long ago in the 1930s. And as you can see, this calculation is not very easy, and as a result it's not frequently covered in many of the StatMech courses that we teach. But I feel that it's important to discuss this, because people very quickly discuss Pauli paramagnetism, which is mathematically easier, and then they stop at that. They don't teach Landau diamagnetism. So that's because it involves reckoning with Landau levels and their associated degeneracies, and this Euler-Maclaurin formula, which is a very unusual and unfamiliar mathematical tool which appears to be necessary in this calculation. So given all these facts, that it's not surprising that many courses kind of gloss over this result. So I felt that it's important to include this to make this course a bit different from what's usually out there. Okay, so I hope you enjoyed this particular portion. So if you really, I can understand if you didn't understand everything, so you should work out all the steps on your own. Just pause and rewind and work out all the steps on your own, and we'll meet for the next class, which is something slightly simpler, which is Pauli's paramagnetism. Thank you.